is super loud.
Great. Three minutes early. Wow.
I know.
Nice job. That's being eager.
But it's also us just making sure everything works.
Right. Hopefully no more unplanned silences.
Yeah. All right.
Okay, should I
Hold on
screen share?
1 second.
Sure.
Okay, cool. So Spotify is like a good
What was
volume.
that?
I went on Twitch to see
whether this time we actually have some background
yeah,
music.
so it's playing. I can't hear it. It's just playing on Twitch, and then it's supposed to just loop. So I made.
And you got it like not too loud so that
Yeah.
our pearls of wisdom don't get drowned into lo-fi beats. It would be a shame. Good. I'm gonna pretend that I hear the music and move a little.
Except I don't even have up until now I didn't have our faces on the stream. So you were just like behind the window. All right, so how do we want to do this? Should I share my screen, I guess?
I mean,
or do you want to share
set up for it, so I can do it.
Share your screen.
I should start at least.
Sounds good.
Look at that. So prepared. Wow. So I promise for everyone who's watching, I promise I didn't actually prepare. The only thing that I did was run this first cell and make the authentication happen so that the notebook is now in our Google Drive and that the Google Drive is mounted in the file system like we have done so many times before. Yeah, the copy of the notebook is already in the drive. That's really all. And I have not peeked ahead. I haven't been a good student. I didn't read ahead. I actually don't know what this lesson is about. Oh, I did one more thing, maybe as a for your information, interesting thing if you're going through this course. We've been watching the videos on here, which is kind of nice because you have some information in the questionnaire next to it. But actually, if you just open it up in YouTube, you get timestamps, just like we put onto our streams. Timestamps, which makes it a bit easier to jump around. Because last time we stopped about halfway, which is when he finishes with one of the notebooks, I guess, and then started, and now he's starting the next one. But we decided we're gonna try to, instead of watching the lessons, read over the book this time. And what you say, Nick? Should we do this? Just switch off. Like I read a paragraph, we talk about something interesting, or if there's anything interesting to say, and you do the next one.
Yeah,
we run the code.
Sounds good.
Cool. All right. Without further ado, let's get started, huh? Okay, so we're on lesson 4. Let me see. We're on lesson 4, and what I think I know about this lesson is that he's going to go a bit deeper.
So, just to interrupt you, Martin.
Thank you. Anytime.
Because I'm the only one who sees the chat too. So Raz is in the chat and he says it's glad to hear your voice.
Oh, hi Raz. Glad to hear your chat. Hear your chat message relayed through Nick. Because I'm screen sharing, I don't actually, and I have just a small computer. I don't see any chat stuff. Well, gonna improve on that at some point.
We really do. Anyway.
All right, but let's get started with this lesson. Okay, so we got the notebook, like the Fast.ai library is set up. We're just running this first cell, and now we're gonna import some stuff, and I get started reading. Yes. Okay. I think you should start this first because I've been talking so much already.
All right, cool. So you're gonna follow along as I'm reading, and you're just gonna scroll for me?
Mm-hmm.
I love it.
You got your own personal scroller.
Oh, this is wonderful. I don't know how I'm gonna do it after this stream. We're just gonna have to zoom from now on and have you as a personal scroller. All right, let's get into it. All right, under the hood, training a digit classifier. Okay, having seen what it looks like to actually train a variety of models in chapter 2, let's now look under the hood and see exactly what is going on. We'll start by using computer vision to introduce fundamental tools and concepts for deep learning. To be exact, so there will be words mispronounced, full disclosure. To be exact, we'll discuss the roles of arrays and tensors and of broadcasting, a powerful technique for using them expressively. We'll explain stochastic gradient descent, SGD, the mechanism for learning by updating weights automatically. We'll discuss the choice of a loss function for our basic classification task and the role of mini batches. We'll also describe the math that a basic neural network is actually doing. Finally, we'll put all these pieces together. In future chapters, we'll do deep dives into other applications as well and see how these concepts and tools generalize. But this chapter is about laying foundation stones. To be frank, can you move the cursor, Martin?
Oh, that.
That also makes this one of the hardest chapters because
Okay. I was just employed for scrolling. I didn't know I have to move the cursor if necessary.
I think you can make the cursor disappear as well.
If I shake it a lot?
No,
I can make it bigger when I shake it a lot.
All right, so to be frank, that also makes this one of the hardest chapters because of how these concepts all depend on each other. Like an arch, all the stones need to be in place for the structure to stay up. Also, like an arch, once that happens, it's a powerful structure that can support other things, but it requires some patience to assemble. So let's begin. Okay. Consider how images are represented in a computer. Pixels. The foundations of computer
Wait, now
vision.
It's my turn.
Oh, it's your vision. I can't scroll though.
That's okay. I can do it.
Okay.
Pixels, the foundations of computer vision. All right. Is there anything like sum up wise that you want to say about this? No. It's just an intro. Let's not.
I got the easy one.
Okay. I'm gonna have to explain what a pixel is. Okay, the foundations of computer vision. In order to understand what happens in a computer vision model, we first have to understand how computers handle images. We'll use one of the most famous datasets in computer vision, MNIST, I believe is what it's pronounced, for our experiments. MNIST contains images of handwritten digits collected by the National Institute of Standards and Technology, NIST, and collated into a machine learning dataset by Jan LeCun and his colleagues. LeCun used MNIST in 1998 in LeNet-5, the first computer system to demonstrate practically useful recognition of handwritten digit sequences. This was one of the most important breakthroughs in the history of AI. That's all.
All right.
I do want to say something about this. I thought for myself, it was quite a mind blow when I understood how images are represented on a computer, that it's actually just like a collection of numbers, each of the pixels being a number, like a collection of numbers of what colors go into making this pixel a thing, and that you can essentially have like a matrix of numbers that represent an image. That was quite a revelation for me. Thank you. Personal story by Martin. Scroll. Let's move on.
All right. Sidebar: tenacity and deep learning. All right. The story of deep learning is one of tenacity and grit by a handful of dedicated researchers. After early hopes and hype, neural networks went out of favor and out of favor in the 1990s and 2000s, and just a handful of researchers kept trying to make them work well. 3 of them, Jan LeCun, Yoshua Bengio, and Geoffrey Hinton, were awarded the highest honor in computer science, the Turing Award, generally considered the Nobel Prize of Computer Science. In 2018, after triumphing despite the deep skepticism and disinterest of the wider machine learning and statistics community, Geoff Hinton has told of how even academic papers showing dramatically better results than anything previously published would be rejected by top journals and conferences just because they used a neural network. Jan LeCun's work on convolutional neural networks, which we will study in the next section, showed that these models could read handwritten text, something that had never been achieved before. However, this breakthrough was ignored by most researchers, even as it was used commercially to read 10% of the checks in the United States, which is kind of cool. Yeah.
I mean, it's weird that you still have checks, but apart from that, that's cool.
I still write checks. What are you talking about?
Keep going.
In addition to these 3 Turing Award winners, there are many other researchers who have battled to get up to where we are today. For instance, Jürgen, you will pronounce this.
Jürgen Schmidhuber, maybe, if there should be dots on his U, I'm not sure.
Probably. Who many believe should have shared the Turing Award, pioneered many important ideas, including working with his student
Sepp Hochreiter
on the long short-term memory, LSTM architecture, widely used for speech recognition and other text modeling tasks, and used in the IMDb example in open close bracket.
You don't have to. I think this is stuff that gets rendered in the book as like an example that links to somewhere else, probably.
Probably.
Because we've seen it before, and I spent like waking nights figuring out what's going on.
Perhaps most important of all, Paul Werbos in 1974 invented backpropagation for neural networks, the technique shown in this chapter and used universally for training neural networks. Werbos, 1994. His development was almost entirely ignored for decades, but today is considered the most important foundation of modern AI. There's a lesson here for all of us. On your deep learning journey, you'll face many obstacles, both technical and, even more difficult, posed by people around you who don't believe you'll be successful. There's one guaranteed way to fail, and that's to stop trying. We've seen that the only consistent trait amongst every Fast.ai student that's gone to be a world-class practitioner is that they are all very tenacious.
Generally, I think a good
just
feature to have if you want to learn something.
I think just to summarize that, it would be Martin gets to pronounce all the German names.
No, but this is interesting, right? That they actually
that this
really was the
cool.
First AI application that was actually run in, I don't know, they say production if it happens in real life.
Yeah, but that was in the 70s, right? Is that what he said?
No.
Go up.
Was it?
Handful of.
So they fell out of favor in the 90s and 2000s. So that must have been early 2000s. Jeff is...
Interesting.
I wonder why.
Yeah.
When.
Anyway.
I wonder. I think it's in the like early 2000s. Anyways.
Oh, well. Anyway.
And sidebar. Yeah, okay, so that's the sidebar, I see. Okay, for this initial tutorial, we're just going to try to create a model that can classify any image as a 3 or a 7. So let's download a sample MNIST that contains images of just these digits. Okay, so instead of just classifying any, no, don't do this. Any digit, we're just going to do 3 or 7, I guess. And yeah, while I was cleaning up some of the notebooks, Nick, I saw that I thought about this a bit. I believe that they have data sets that come imported or at least the URLs to them, because also the pets dataset was similarly in there, urls.pets, this all caps. All right, I
Sorry,
got it in, I think.
Jonah Vision's back and I'm responding in chat.
Oh, hi.
Hello.
Good job for figuring out the deployment.
Yeah.
I just read on Twitter. I'm excited to. You should tell us how you did it. I have not figured it out yet, but I didn't manage to put any time into it since the stream.
Yeah.
But pretty cool.
We both kind of took the weekend off.
I just had one day, but one day.
One day, I mean, yeah. Well, off from this, I mean.
Yeah, that yes. Okay, so we got the path to all of the pictures. I guess there was some nice image somewhere here. Skipping ahead. Okay, this is how they're gonna look like. Bunch of handwritten digits and path. All right. What are you doing here? Path.base path equals path.
Yeah, and it's just path is the on
But
target.
what's that about? I mean, he's using the Python pathlib like an object, and then he's setting the base path for that object to where these sample digits are. But he didn't even I don't think he anywhere defined a path object yet. So that's just, maybe that's a setting you can put on, like if you import path and then you can set it for the general everything you're going to run with this is going to have this as the base path.
Maybe.
Sounds cool if it works.
Yeah. Oh yeah, there you go. There's in the next one.
I wouldn't know what else it does. Is there an expression? Oh yeah. Okay, we can see what's in this directory by using ls, a method added by Fast.ai. This method returns an object of a special Fast.ai class called L, of course, which has all the same functionality of Python's built-in list, plus a lot more. One of its handy features is that when printed, it displays the count of items before listing the items themselves. If there are any more than 10 items, it just shows the first few. Okay, that's nice. So let me play around with this a little. I just want to see whether this is going to give us the same result. No, okay, so this is because it set the path to be this. I wonder what it is. Dot. Wouldn't that mean it should be there? Let me see. Path, base path. Huh. So it seems to say that this is where we are, but if I ls where we are, I actually get a different output. So yeah, some interesting setting must have happened with this. What's that? Is that Rex? What's going on? I see you responding to the...
I turned the mic off in the stream because an ambulance went by the street and my dog likes to howl at all the ambulances.
But you just told this to me now.
No, I unmuted.
Oh, you unmuted. Okay, good.
For context.
Okay, so this is interesting for me, but maybe it's not that interesting. Is it interesting? Like this is setting something up here. I don't really understand what it does, but this Python pathlib is pretty cool. So it does something pretty cool here. And by defining that it's going to pretend to be at this certain location that we got back from the MNIST sample untarring. But it's different than if I use bash to check where we are. Like it lives somewhere else.
Yeah, did you run that next one?
Yeah, sure.
Path.ls?
Oh yeah, I think I did. Another thing we could try is path. I think there's something like apps path, where maybe it's gonna give us the actual location of it. No, it's not called apps path. Apps _ path. No. Or maybe it's just apps. Apps. I know it exists.
Was there
It
something
might be
like
an attribute. Maybe I should look it up, huh? Absolute. All right, gotta call it. And here we are. Yes, okay, dot. Perfect. Oh, it's actually a face.
it's a surprised face. It's like, ooh.
All right, I take it.
Can you try abs path without the brackets?
I tried that.
Oh, you did?
But I happily try it again for you.
No, without the underscore.
Also that?
Yeah, Jonah Vision just put that in the chat. Let's see. Oh.
Yeah, no, it doesn't. I think that's something that works with OS. If you use the OS module, then that's also why I was mixing them up. But it's on pathlib, it's absolute, and that's a method, but it still just gives us this cute
and
face.
Then abs path with the parentheses, still nothing, right?
No, they all fail, yeah.
Oh.
Like, also it wouldn't, like, if it would be a method and we didn't call it, we should get we shouldn't get an error, right? So if I say absolute, which actually is a method on the path, then we're not going to get an error. It's just going to tell us this is a method. And if you want its results, actually it's already giving us the results here, but we're not calling it. So yeah, it's just a mix between this OS module and pathlib.
And abs path without the underscore. Oh,
yeah, we tried that too.
I see what you're saying.
We tried all of those, yeah.
I see what you're saying.
Okay, so anyway, there's some magic going on here.
Yeah.
I wonder what it is, and I'm gonna move on. Okay, so somehow this path thing knows where it is, and it has access to all of the stored mnist things. Well, what it has access to is a labels.csv file, a folder called valid, and a folder called train. All right. The mnist dataset follows a common layout for machine learning datasets, separate folders for the training set and the validation set, or test set. In this case, it seems we don't have a test set. Let's see what's inside the training set. Shoop. Inside we have training, okay, another folder 3 and another folder 7, which is, we could look deeper, I guess. No, not like that. And then probably have a bunch of images in there, yeah. A lot of images that all represent a handwritten 3. There's a folder, okay, I just talked, right, I could just keep reading. There's a folder of 3s and a folder of 7s. In machine learning parlance, we say that 3 and 7 are they, do you want to do this word, Nick? Parlance?
I don't think I could do it better than you.
We say that 3 and 7 are the labels or targets in this data set. This is something I've learned with this course already, that like just putting stuff into folders and giving them names is the easiest way to label a data set.
Yeah.
Right. It's nice. Let's take a look in one of these folders using sorted to ensure we all get the same order of files. Okay. Yes, I guess we just did that. As you might expect, it's full of image files. Do you want to take over? I've been talking for a while.
Sure.
All right, here you go. And you can use my fingers. You can remotely control my fingers if you want to type something.
Okay. No, you can type all that, because I've been so disconnected from Python for like years.
All right.
That, like,
yeah. Okay, so then you just give me tasks. You're like, look at this, and then I have to figure out what I have to do, and probably don't know how to do it.
Like, okay, Martin, scroll.
Wait, how? Up, down?
Not too much. All right, as we might expect, it's full of image files. Okay, let's take a look. So image im3 path equals 3 is 1. Okay, then that's the first image. Got it.
That's just after the sorted one.
Right.
image
Can
3. Did we save
put,
this
like,
somewhere?
10 or something? Like, let's see what else is in there. Let's see another 3.
Yeah, sure.
Cool.
Oh, very different.
Yeah.
Different style.
Mm-hmm.
What about 100? Another different style.
Interesting. Okay.
Any other number, Jonavision or RAS that we should check out? If we're still around, I don't know.
Let's see.
One, two,
Let's
three.
just keep. Yeah. Let's just. Oh, yeah.
Keep going. Oh, I want to do number 3. Let's see how the third 3 looks like. Beautiful. It's like a beautiful 3.
Wouldn't the third one be 2?
Oh, you're right. Ooh, burn.
Ooh. I like
the other one more.
I like the other one.
Yeah.
All right. Here we're using image class from the Python image library, imaging library, which is the most widely used Python package for opening, manipulating, and viewing images. Jupyter knows about PIL images. PIL. Is it PIL? PIL? You don't know. PIL. PIL.
Yeah.
PIL images. So it displays the image for us automatically. In a computer, everything is represented as a number. To view the number that would make the image, we have to convert it to a NumPy array or a PyTorch tensor. For instance, here's what a selection of the image looks like converted to a NumPy array. I always thought that was NumPy when I first saw it. And then we started using it. I think it's NumPy. Yeah. Okay, so array M3.
Here's my beautiful mind blow.
Right.
It's just a.
Well,
it's
now
just
you have
an
to
array
run
of
it again
numbers.
because we
All matrix.
reassigned image 3. We reassigned M3.
Did we?
Yeah.
Yeah. So it's going to be different.
This is a new 3. Ooh.
Look at that, completely different. There's all this black around here where the other one had
Wow.
already like a. Let's look at the whole one, huh? Or do you think it's too big? 4 to 10. Oh, it's gonna be too big, yeah.
So
But let's look at
yeah.
a little bigger. Maybe 10. So what's the first? What's the second? 4. 1, 2, 3. What was it before?
4.
4 and 10.
4.
No, 4 and 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is 6 times 6. 4, 10 is 6 times 6.
I mean, 6 is 36.
I'm confused.
Yeah.
1, 2, 1, 2.
The 4. Okay, why don't we just.
So this gives us one number.
The 410 indicates we requested the rows from index 4 to 10.
If I just did my scrolling job well, everything would be fine, huh? All right, I'm still gonna play around. Keep reading.
Okay, hold on. 3s is an array of images of 3, so all indexes should be pictures of 3s. So IM3 is one of those pics of 3s. Yes.
Yes.
Length of 3s is equal to 61.
Yeah, they're all images of 3s.
All images of 3s. Yeah,
Yeah.
And then if you scroll up, right, and then we have all images of 7s.
Right. In this folder, we'd have a bunch of.
Do you want to just
bunch of 7s?
Yeah.
Should we look at one?
Sure. Yeah. Duplicate that.
Is that it? Mirror cell in tab. No, I don't think so. Copy. And then can I paste it? Yeah, works. Okay.
Yep. And then.
So that would be image 7, and we get 7s, and we look at the 7th one.
Ooh.
Oh yeah, if in case someone this is a nice multi-cursor on Jupyter Notebooks.
Are you just holding Option? Is it the same?
Yeah, Option. Mm-hmm. Yeah, you just hold Option, then you can make a bunch of them.
If you hit B, it makes a cell below when you're not in edit mode.
This works with Jupyter notebooks usually, but it doesn't seem to work always with collabs for me.
Yeah.
Like when I do it, so now I'm in edit mode and I hit B, and then it just, it goes to really weird places. You know, like this goes all the way to the bottom. So I kind of stopped using it because it's super annoying to how it jumps around the notebook.
Yeah.
I mean, maybe I need to click here first and then B. No, wait, no, that was wrong. Escape, and then maybe I try once more. Yeah, it's confused. Yeah, it doesn't work the same way as it does in the normal Jupyter notebooks. The shortcuts are a bit nicer.
Yeah. Anyway.
Okay, so here we've got the 7th 7. A little hook on the front. But yeah, that's it essentially. We have these 2 folders, and one of them contains a bunch of images of 3s, and the other one a bunch of images of 7s.
Right. Cool. So
okay.
So the 410 indicates we request the rows from the index 4 included to index 210 not included, and the same for the columns. NumPy indexes from top to bottom and left to right. So this section is located in the top left corner of the image. So 410 top left, right. Here's the same thing as a PyTorch tensor. Okay. Ah, there we go. We started.
That's it. There it is.
3. Yeah. Very cool.
10 to 40. That's the bottom of the 3, I guess, right? So if you wanted to get more, so wait, it said before that we got the top left corner. Did it say that with the 4? So if I go 0, I should go to the very top left. 040. Should get a different slice. That, yeah, nice.
Yep. Oh, you can start seeing the full.
Yeah, that's nearly all of it actually.
That is actually all of it, I think.
Yeah. Oh yeah. There you go.
Cool.
Nice.
Okay.
It's probably not even 40 wide. 40 pixels wide. Probably less than that.
Can we? Oh, you're doing.
Oh, you're indicating some scrolling, huh?
Seems like.
I was just trying to see if I can narrow down the dimensions. All right, I'm scrolling.
All good.
Sir. Okay. So yes, we can see a corner of it. Okay. Got it.
Whatever. We can slice the array to pick just the part with the top of the digit in it and use a pandas data frame to color code the values using a gradient. Okay, that's kind of cool. So that's going to use like the value where 255 is the highest and then 0 is black. But it's interesting because it's the opposite, right? So
what do you mean?
0
yeah 0 is actually black. Yeah it turns those around. Interesting. Nice.
Can you, I mean, just, I don't know if it's going to work, but can you change the word grays to like blues and what other?
Yeah. I think I wonder what we can do. Is this a matplotlib function or background gradient?
It's a pandas, it said.
Data frame. It's a pandas function. Okay, let's try being good and actually looking at the documentation, which would work with data frame dot background gradient. Okay, so we want to learn about this one, and then we can say doc and there it is. Styler.background gradient. Column map. Poo-poo. Poo-poo is the default. I guess we can try that one out.
Okay.
Oh wait, so column map string or column map matplotlib column map? Matplotlib color map. So any matplotlib color map, I guess, would work. Is there any examples in there? Doesn't look like it. So let's see what there is. Lots of fun stuff.
Mm-hmm.
Sequential 2, diverging, cyclic. Are these the names or?
No, this would be so sequential. Then there you go,
Ah,
like blues and stuff, and then
great.
sequential
So
two.
yeah.
So
Your
let's
blues
look
would
at
have worked.
Yeah,
Yeah.
but that seems boring. Let's do something more exciting. Scroll down.
What about Poo Boo?
Let's test that one too. But what's in the diverging one? I feel like
Diverging. Let me make this a bit bigger. Diverging. Puke. Purgen.
okay.
Pink, yellow, green.
Let's do Poo Boo, and then try like
Puke. Okay. Poo Boo.
That's kind of cool.
That's a
I like that one.
nice blue one. I like it too.
Hot.
What? Hot?
I'm just thinking. Yeah, all lowercase.
Like that?
Yep.
That was one?
Yep.
Oh.
Interesting. Okay.
And that's more,
Yeah.
how the actual image looks like. Where do we have it? And sidebar. I'm too far. There it is.
Yeah. Try.
I want to try P. Was it that? Puke. Pink, yellow, green is my guess.
Mm-hmm.
Descriptive, even though it's so abstract.
Can you try like winter?
Are you guessing these or
No.
you looked them
I
up?
remember all of the seasons are one of them. So there's, I remember seeing autumn, winter.
Let's do an autumn one then, considering that that's the
We
season
are
I'm
in
sitting
autumn.
in. Beautiful. All right.
I think Poo Boo is my favorite one so far.
Is it? Okay. Poo Boo. All right, let's move on.
Okay.
Yeah, that's cool. Yeah, I mean, we can see the 3. We saw it before.
This is all of your documents.
This is my doc. Yeah, let's get rid of it.
Okay, that's a photo
Okay.
of how it's with the grays. Okay. You can see that the background white pixels are stored at the number 0, black 255, shades of gray are between the two. Okay, the entire image contains 28 pixels across, 28 down.
There you go.
For a total of 784. Okay, this is much smaller than the image that you would get from a phone camera, right, which has millions of pixels. But is a convenient size for our initial learning and experiments. Cool. And then you build up to larger full color images. So now you've seen what an image looks like to a computer. Let's recall our goal. We'll create a model that can recognize 3s and 7s. How might you by going, okay, warning. Okay, so how...
Warning, stop and think. Before you read on, take a moment to think about how a computer might be able to recognize these two different digits. What kinds of features might it be how might it be able to identify these features? What kinds of features might it be able to look at? How might it be able to identify these features? How could it combine them together? Learning works best when you try to solve problems. Someone else's answers. Step away from this book for a few minutes, grab a piece of paper and pen, and jot some ideas down. Let's do it. Text. Here's our piece of paper. Here are your fingers. Any ideas you want to jot down? Wait, are you already typing? I can't interpret that.
You have to change your keyboard though to like the American.
Yeah, then I keep mixing up the Z's and Y's. So what the question, things to think about. What kind of features might I be able to look at? Obviously, like the color, like the numbers, color codes, numbers, features, edges.
Mm-hmm. Edges, corners, circle, like roundness.
Corners. What else?
So like the round part of it. So
Well, which
in this case,
so like that's a feature.
This could also turn into a 7, right? So it would be like the round, and then how it kind of like jumps back in.
This down there.
Yeah, that could tell me.
That would disqualify it as a 7, right?
Right, but it could keep it qualified as an 8. because you have, 2 3s or an 8.
Let's look at the whole picture actually. 0, 28, 0, 28. Okay. Yeah. I mean, so you're thinking it's like this larger scale things, like, okay, so it can recognize that there is a band into this direction, then there's another band into that direction. This moves up, or do you think it's like about, okay, there's a large difference between 0 and 254. There's a less intense difference between 0 and 18. There is no difference between 0 and 0. That's like stuff that I mentioned.
Yeah, I think that's part of it, right? And then it like.
And then what is next to each other?
Creating that edge, right? And you can see like 0 and 254, you got that big drastic change. And I think it seems like that's like a straight line, right? Where there's, because even like if you're in Photoshop or something, when you zoom in,
you just froze for me. Sorry, I didn't hear anything for a couple of seconds.
Okay, so if you scroll up a little bit, the 0 to 255, that to me tells me that it's a straight line. Anything that has this increasing gradient would tell me that it's on some sort of a curve. And that like checks out with, whenever you're like editing photos on Photoshop or something, you zoom all the way in, the straight lines are always, because it's a box, right? So a straight line can have that solid edge on horizontally or vertically, but a corner always has some sort of gradient to make it look more
fussy
natural.
Stuff.
Yeah. Unless like you remove all this other stuff, but then it doesn't look like it's not a natural 3.
Like, I mean, we can, the nice stuff is we could like zoom out here, I guess, right? And then it looks like we even get the idea of it looking more.
Sure.
Right? Like the corners, if you would take those out. Yeah. So that's a good point. I think we have, like, if we have fuzzy stuff, like if the differences are not as big, it means it's indicating there's a like a curve. And if we have a stark difference, we have a straight line.
Mm-hmm. But also to consider, like, if there was ever something like maybe a 7 could have a perfect 45-degree line where there may not be any gradient on either side. But I don't know.
Well, a 45-degree, could still work theoretically. That's true, yeah. Would it though? I don't think so. Like, I think the pixel, like if you actually have a straight line, like if you have a 45-degree angle line, you're gonna get these kind of things.
I would think so too, but that's just something that, I'm thinking of, well, how could you, so my question is, how could you create because you could create a 7 with just a horizontal line and a 45 where there would be no gradient whatsoever. But it's hard to make, a 3 is, you could do that with a 3, but it's very like,
it would be like jaggy,
like stone chiseling type 3.
Zack. Yeah, true.
So
okay, so maybe but we can't qualify, but we can't say that something is going to be a 7 because it doesn't have any round, that something is a 3 because it has gradients, right? Because the 7s can be hand drawn in many ways so that they would still not be these perfect angles. All right, let's write that down. Any other thoughts?
So Raz chimed in and said anti-aliasing.
What's that? What is that?
I don't know. We'll wait for a response. I also think that softening of edges is called anti-aliasing to make them look natural. Okay, cool.
So that would be if you have so that's like making this in between numbers essentially. Like you have strong difference, and then you click on, no, that's not blur, would be blurring. So it's like a technique you can do on images to blur edges.
Mm-hmm.
Gotcha.
It's pretty cool.
So that's not necessarily something that we can, like, something that would happen, a kind of feature. That's just more of a technique that.
So let's see, edges, corners. I guess edges we can also, corners, and I don't know how you would say, like, round features.
Edges as a roundness.
Sure. And then that plays into some, so because there's, if we go back to, before we get too deep into this.
Wait. Let me just, because this is all pretty much the same, right?
Well, so hold on. Like, that's what I was about to get at. Before we get too deep into this, let's look at the question again, right? So the first part is, what kind of features might it be able to look at? And I think we have, I think edges, corners, and roundness can be features. And then how might it be able to identify these features? And then, that's where we can say recognizing some sort of like anti-aliasing or something like that, right?
So since I don't know this is this like a, is it a technique that is like done for identifying features? But because to me it sounds more like it's like an image editing technique, like something you do to apply some sort of filter essentially on the image. Let's see what Russ says.
Yeah.
What kind of features? So what I was also thinking is like position, right, of elements. Position of where is a high value, where is a low value. That's going to be different for a 3 and for a 7, and because it, like, the computer is always aware of this whole matrix. It knows that this location is 8 and 10 or something, right? So it can learn that usually when you make a 1, right, there's never anything on. I mean, there can be, but I guess it's rare that the 1 is drawn over here or something.
Well, so to answer the anti-aliasing question, it's something that editing software or the camera or 3D rendering software does.
Right. Cool. So it's not necessarily something to identify, but it's an image editing technique.
Yeah, the software just applies. That's just what the software does. Yeah. So going back to what you were saying, I think this may work on these like smaller images, but if we had like a larger image that we were trying to get, or more pixels that we were trying to identify a 3 or 7, then that wouldn't necessarily work, right? Or we would have to combine that idea with because we would almost like take little snapshots or like a window of, scroll up a little bit, like, maybe the first 10 by 10 we would take, right? And then I
think that's actually how it works. Like, I think it applies this like mask over it and then moves this mask around.
And then maybe like stitches the information together and then sees like, okay, well, we got this in this little part. What does that mean connected to this? Oh, now we're starting to see this.
And then if you would have a higher resolution image and they would apply the algorithm on it, it would just calculate, I guess, the ratio between, like, if you have this is 28 times 28, what you train on, the other one is like 1,000 times 1,000, then it just takes like a similar,
like millions of pixels.
Right. And it just takes a similar ratio of the window that it looks at and decides, is there something or not, I think.
Yeah, it could. That kind of depends on like how quickly you can. I think that's something that you can kind of mess around with, right? Like, can you increase the window size, and how would that?
Don't cry.
I'm not crying. I'm very close to crying. No, like what I'm saying is could you increase the window size or increase the number of windows, and which one is more optimized? If that makes sense.
Okay, it makes sense. My thought was like if the algorithm records that in window number 6, all right, window number 7, whatever, should have this amount of like these types of values, or should never have these values. It's not that strict. I'm aware of that. I'm just saying like it could learn something that usually in window number 7 there's nothing when it's a 1, right? And then if you have a larger pixel image, it could still say, okay, window number 7, because it scaled up the amount of pixels that are in one window in a ratio that makes sense to what it was initially learning.
Yeah.
Is that confusing?
Yeah, I think it depends on like the system constraints, right? Like if you can learn, if you have like a powerful, if processing power is not an issue, then you can increase the window. But if you have limited for like a million image and a million pixel image, and you're trying to learn across thousands of images, right? You may run into some sort of a bottleneck in processing power, but if you can decrease the window size and then just optimize for memory, then that may make it faster.
That totally makes sense. I was thinking about classification actually, not about the learning. Yeah. I was just thinking when you feed it something to classify. Yeah.
Mm-hmm. Okay.
What kind of features might be able to look at? Edges, roundness, corners, position. How might we be able to identify these features? Changes. What did we talk about? Changes in numbers next to each other, or in a window size. How could we combine them? Combine what? The features. How could we combine them from left to right? I don't know what it means.
I think I'm just going to like blanket that and say it has something to do with like
blank.
Like
goes blank.
The blanket.
A blanket. All right, go ahead.
And just pull out the magic like card and be like, you know what, this has something to do with the way that the algorithm handles back propagation and brings things back and combines everything together. And I could be wrong, but at least I have my blanket.
Propagation. I lost it. Nick has a blanket.
Nick has a blanket.
Okay, let's move on.
Safety blanket. All right, now let's learn.
First try pixel similarity. Okay. So here's the first idea. How about we find the average pixel value for every pixel of the 3s, then do the same for the 7s. This will give us two group averages, defining what we might call an ideal 3 and 7. Interesting. Then to classify an image as one digit or the other, we see which of these two ideal digits the image is most similar to. This certainly seems like it should be better than nothing, so it will make a good baseline. That essentially just says how much color, does one of the digits need, right? Like if you average over all pixels, like how much a 1 is going to have less than a 3 because the 3 covers more ground when it's drawn. Is someone chatting?
No, I'm getting distracted.
You're like on social media?
No, I was making sure that anyway, whatever.
Cool. Okay. Yeah, we didn't think of that. Averages. It's an interesting point. Jargon. Baseline. A simple model which you are confident should perform reasonably well. It should be very simple to implement and very easy to test, so that you can then test each of your improved ideas and make sure they're always better than your baseline. Without starting with a sensible baseline, it is very difficult to know whether your super fancy models are actually any good. One good approach to creating a baseline is doing what we have done here. Think of a simple, easy to implement model. Another good approach is to search around to find other people that have solved similar problems to yours and download and run their code on your dataset. Ideally, try both of these. Step 1 for our simple model is to get the average of pixel values for each of the two groups. In the process of doing this, we will learn a lot of neat Python numeric programming tricks. Let's create a tensor containing all of our 3 stuck together. We already know how to create a tensor containing a single image, to create a tensor containing all the images in a directory. So tensor is just a multidimensional matrix, right? Is that, yes?
Yes.
To create a tensor containing all the images in a directory, we will first use a Python list comprehension to create a plain list of the single image tensors. Plain list of the single image tensors. We're going the way in this case, making sure that the number of returned items seems reasonable. So it's taking all of the numbers, all of the tensors in each of those and putting them into a list. Image open. Okay. I'm making 2 of those lists. Let's see how fast this is. Fair enough. 6,131.
Right, that's the
images.
So that's the number of that's the number of 3s and that's the number of 7s. Cool.
Note, list comprehensions. List and dictionary comprehension, a wonderful feature of Python. Many Python programmers use them every day, including the authors of this book. They are part of the idiomatic Python. But programmers coming from other languages may have never seen them before. A lot of great tutorials. Okay, I'm going to skip that. Yes, list comprehensions. We also checked that one of the images looks okay. Since we now have tensors, which Jupyter by default prints as values rather than PIL images, which Jupyter by default will display as images, we need to use Fast.ai's show image function to display it. Okay, let's look at what it looks like without that. Nothing. I think this, yeah, okay.
So it's going to be the same thing.
Show image, I think. Is that what it was?
Okay.
And I think this, like adding this comma thing that's some Jupyter Notebook stuff where then it doesn't print out this, I believe, but only it kind of like hides some type of output.
Got it.
Maybe the return output or something. Okay, show image. Nice. Okay. Go ahead. You read something.
Okay. For every pixel position, we want to compute the average over all the images of the intensity of that pixel. Got it. We want to compute the average over all the images of the intensity of that pixel. Got it. Okay, interesting.
Okay, that's cool. I didn't think that's what they're doing.
To do this, well, that goes back to like what you were suggesting up there, where like
position.
If the 3 starts here, it should start here everywhere. But I guess for the numbers, it's easier because you can, in this data set, right, when you're learning this stuff, they've cropped the images to try to be the one to be almost in the middle and you know. But anyway, okay. To do this, we first combine all the images in this list into a single 3-dimensional tensor. The most common way to describe such a tensor is to call it a rank 3 tensor. We often need to stack up individual tensors in a collection into a single tensor. Unsurprisingly, PyTorch comes with a function called stack that we can use for this purpose. Some operations in PyTorch, such as taking a mean, require us to cast our integer types into float types. Since we'll be needing this later, we'll also cast our stacked tensor to float now. So casting in PyTorch is as simple as typing the name of the type you wish to cast and treating it as a method. Okay, generally, when images are floats, the pixel values are expected to be between 0 and 1. So we will also divide by 255 here. Okay.
Okay.
Pretty straightforward.
I think is that what's called one-hot encoding? That you take some value that is somewhere and then you re-encode it to be between 0 and 1, I think.
It's called one-hot encoding. Okay.
Pretty hot.
Pretty hot.
Okay. Happy with that. Torch size. So now it's got the shape. Wait, so what did we do?
So now you
This
just
is the amount of
changed all
images.
the pixel values from between 0 and 255. Now it's between 0 and 1.
Yeah. Okay.
For 3s and 7s.
And it's in this different it's in this different structure.
Yep.
That it's a single 3-dimensional tensor that has somehow, whoa, this is hard to picture for me now. So it has 3 dimensions. 2 of those 3 dimensions seem to be the like X and Y values of the images, right? That's the 28 pixels times 28 pixels.
Mm-hmm.
And then the 3rd dimension, or first, is the images themselves. Like that's the amount of images that exist.
So let's let's see if this
Read on.
Yeah.
Okay.
So perhaps the most important attribute of the tensor is its shape. This tells you the length of each axis.
I guess this book is well written, right? Like the questions that come up get answered in the next paragraph. I think that's generally a good educational thing.
In this case, we can see that we have 31 images, each of size 28 by 28. There's nothing specifically about this tensor that says that the first axis is the number of images, the second is the height, and the third is the width. The semantics of a tensor are entirely up to us and how we construct it. As far as PyTorch is concerned, this is just a bunch of numbers in memory. The length of the tensor shape is its rank. Okay.
Okay. And the shape of the 7s is also going to be 3.
Yes. This is this like rank
Not
3.
7. Yeah.
Rank 3 tensor. Yeah. Okay, cool.
Okay. I don't really understand rank 3 tensor so far, but I'm fine moving on.
Okay. You want to read this one?
No, go ahead.
Oh, okay.
You didn't want to.
It is really important for you to commit to memory and practice these bits of tensor jargon. Martin. Rank is the number of axes.
He gets me.
Or dimensions in a tensor. Seriously, this is like he wrote this with you in mind.
It looks like it.
Shape is the size of each axis of a tensor. Okay, A. Watch out, because the term dimension is sometimes used in 2 ways. Consider that we live in a 3-dimensional space where a physical position can be described by a 3-vector v. But according to PyTorch, the attribute v.ndim, which sure looks like the number of dimensions of v, okay, equals 1, not 3. Why? Because v is a vector, which is a tensor of rank 1, meaning that it has only one axis, even if that axis has a length of 3. In other words, sometimes dimension is used for the size of an axis. Space is 3-dimensional. Other times it's used for the rank or the number of axes. A matrix has 2 dimensions. When confused, I find it helpful to translate all statements into terms of rank, axis, and length, which are unambiguous terms.
Okay, can you explain rank to me?
No.
Okay, anyone else?
Go up.
What about asking Jeremy?
He gets us. So maybe
Gets us.
maybe
We could watch over that, maybe if it's important or not.
Did we pass baseline model?
Yeah, we just talked. No, we haven't created it yet. We're in there creating a simple baseline model, but I think.
Can you go back and just scroll up? There was something about, and just go to where it says rank 3. The first time it says rank 3 tensor.
Is it that one? No, that's not the first time, huh? What is a rank 3 tensor?
There we go.
There we are.
We want to compute the average over the images of the intensity of that pixel. To do this, we first combine all the images in this list into a single 3-dimensional tensor. Okay, we often need to stack up individual tensors into a single tensor.
So we start with a bunch of images that are, each of them are a tensor or a matrix. What's the difference between a tensor and a matrix?
Go to your second tab.
Oh.
Scroll down a little bit. NumPy array versus PyTorch tensor 11205.
The problem is when I put this on, then no one can hear it. So you should do that. I can send you the link.
Yeah.
Where are you? Chat. Coming up.
Oops.
Let's see what Jeremy has to say.
Okay, hold on. How do we... But you can't hear it. And I have to share my screen again.
Mm-hmm.
Okay, hold on. This is so messy. Where?
Do you have like a lot of screens around, or?
Oh, there we go. Okay. This one. Let's put. There we go.
Okay, cool. Okay.
So do you get it?
It looks like it's just the same, only that you can compute it in the GPU. That's my takeaway.
Okay.
I don't know. So a tensor is, in my head, is still like a multi-dimensional matrix.
Mm-hmm. I'll let you share the screen.
No, wait, you had another, wait, we wanted to watch this other thing. Can you do that too? Like, can you skip to the part where he talks about working with arrays and tensors?
Yeah, so actually the way that we set up the audio this time, the audio from the video, even if I play the video, doesn't get live
doesn't
streamed.
translate.
Yeah, so
Okay.
you can play it on your side.
And then I can make it that it at least goes into the.
Well, just play it and then just put closed captions, and I'll know
Okay.
what it feels like to be Martin for the stream.
I can also put it on my through my mic.
Okay.
It's not really great, but I'm gonna do that.
Well, go ahead, try it, and then I'll adjust the audio on this side, if anything.
Working with arrays and tensors. Let's see.
It's very important before we kind of go too much further to make sure we're very comfortable working.
Raz is heading out.
And they're so similar.
Martin.
What?
We could start with a list of lists.
Sorry, it's just everything's a bit slow.
Yeah. No, I was just saying. Raz was saying in the chat they're heading out now. So.
Okay. Bye. Thanks for dropping by.
Yeah. Thanks for sticking around.
We can convert it into an array or into a tensor. We can display it, and they look almost the same. You can index into a single row. You can index into a single column. And so it's important to know, this is very important, colon means every row, because I put it in the first spot, right? So if I put it in the second spot, it would mean every column. And so therefore, comma colon is exactly the same as removing it. So it just turns out you can always remove columns at the end because they're just implied, right? You never have to. And I often kind of put them in anyway, because just kind of makes it a bit more obvious how these things kind of match up or how they differ. You can combine them together. So give me the first row and everything from the first up to but not including the third column. Right, so that's 5, 6. You can add stuff to them. You can check their type. Notice that this is different to the Python. The Python type. So type is a function. This tells you it's a tensor. If you want to know what kind of tensor, you have to use type as a method. But it's a long tensor. You can multiply it by a float, turns it into a float. To have a fiddle around, if you haven't done much stuff with NumPy or PyTorch before, this is a good opportunity to just go crazy, try things out. Try things that you think might not work and see if you actually get an error message. So we now want to find out how good is our model. Our model that involves just comparing something to.
Okay. I don't know if this gave me what I was looking for, but let's move on with the notebook, huh?
Sounds good.
Okay, I'm sorry, Jeremy. I still don't really understand what a rank is, but one day I shall know. Okay.
All right. Do you want to just continue with this? I'm gonna grab some water, and I'll be right back.
Yeah, but you're gonna miss the important part. Yeah, go ahead. Go,
Okay.
quick. All right. So we can also get a tensor's rank directly with ndim, whatever the rank is. It's probably really easy. Maybe it's just that it's got 3 things. Is that it? I think that's it. Just that there's 3 items. Anyways. Finally, we can compute what the ideal 3 looks like. We calculate the mean of all the image tensors by taking the mean along dimension 0 for our stacked rank 3 tensor. This is the dimension that indexes over all the images. In other words, for every pixel position, this will compute the average of that pixel over all images. That's really nice. The result will be 1 value for every pixel position or a single image. Here it is. Stacked 3s.mean. So stacked 3s is the tensor that has all the information, and then we can just take the mean of it. What's the 0? Stacked 3s mean. What is the 0? You got some info for me? No. Let's see if I can find out some more. Dimension none. Keep dimension false. Dimension 0. I wonder what that means. Okay, that's because I'm calling it. Probably. No. Stack 3s that mean. Okay, so I'm not entirely sure what this 0 means here, but it looks like it is. Okay, should this? Well, anyways, I understand what it does. Okay, so it takes every pixel through this, all of the images. I'm imagining them like sitting behind each other, and it's just poking through each of the pixels and taking the average of everything that it pokes, and then displaying them. Or maybe you shine a light and like it takes all the averages of everything, it shines through. That's actually kind of nice thing. Like it's like a shadow. If you had like all of those images stacked in a row, and then you shine a really, really strong light through it. I got a nice image, Nick. Hi. I was just thinking of how to think about this average. Like if you imagine like you have all of those images stacked behind each other, and then you shine a really, really bright light through it. And then this is kind of like what the shadow would look like. Don't criticize me. Let's just move on. According to this dataset, this is the ideal number 3. You may not like it, but this is what peak number 3 performance looks like. I like it. I think it's a good 3. You can see how it's very dark where all the images agree. It should be dark, but it becomes wispy and blurry where the images disagree. Let's do the same thing for the 7s, but all the steps together at once to save some time. What steps? It's all happening in the same. But put all the steps together at once. This is the same steps. Anyways. Hello, 7. Let's now pick an arbitrary 3 and measure its distance from our ideal digits. My ideal 3. Stop! Stop and think, Nick. How would you calculate how similar a particular image is to each other of our ideal digits? Remember to step away from this book and jot down some ideas before you move on. Research shows that recall and understanding improves dramatically when you engage with the learning process, but yes, we know this. Let's do it. Okay, jot. We want to see the distance. So I would say we can just look at every pixel of the image and see how far away is it, like how far is the number. We know it's just numbers, right? Mm-hmm. So there's a 0 in our example image, and there's maybe a 1 in the, oh no, they're all between 0 and 1. So let's say 0.0 and 0.99 or something in the comparison image, which is the perfect average. So that they don't overlap. They're pretty far from each other, and the difference would be 1 minus the other, and an absolute of it, right? Or something.
So I think if you took, yeah.
Does that make sense? If I took,
I'm trying to think. Because you would have to go through, let's just think of an image as an array. for a
Yeah.
moment, right? With 0 to 1 values. And then if you had to go through each of, to compare the differences or to see how similar it is, you would go one by one, almost take two of the arrays together, right? Stack them, and then compare the index of each of the values, right? And I think when you're comparing the index of those values, you would have a because it's yeah. So could you just do like have a difference indicator somewhere, like another variable set to 0, and then no, that wouldn't work. I was thinking if you just add the differences as you're going through the array, comparing the two, but the difference between, index 10 and index 1 could be the same, but because they're in different positions, it could be a totally different thing. So never mind.
Maybe it's like an absolute, maybe there's like a threshold value or something. You add up all the differences. Like the perfect one says it should be 0.99. Let's say, make it a bit more realistic. Our example 3, these are both 3s, right? Our example 3 has 0.98, so we get the difference here of 0.01, and we keep that around 0.01. Is like a lot. It's like a, I don't know. That's not a loss. I'm sure this is the wrong way to use this term.
Right. I think
mistake, error, difference, 0.01 difference.
So I think we're talking about two different things. What you're talking about is comparing the individual pixels, right?
Right.
And defining this threshold of what is acceptable. I think that's fine. What I was talking about was how do you compare the two different images? So let's say we have like this is a given, right? We have this threshold of when we compare the two images, it's, it's fine or it's not. Right. So like,
but I meant like a threshold for the whole image. Like, for each pixel you do this thing, and then you add together all of the differences.
So here's the thing though. Let's say for the first, just to make it easier, right? Forget about 28 by 28. Let's say the image is represented by 100 elements in an array, right? And the first 50 elements are, the values are 0.5, and the last 50 are 0.0, and then it's inverse on the other one. Those images are literally polar opposites, right? But using the absolute, and then comparing the difference at the end, you would actually see that it's the same image. So that's what I was saying.
I see what you're saying.
There needs to be a way to almost maybe maybe going back to the window approach. If I don't think it.
Or you look really at each pixel, and you just make a decision based on that, or on the window, yeah.
Well, actually, hold on. Let's go back to this for a sec. If the threshold for, maybe there needs to be two thresholds, right? So one being each individual pixel of this 0.01, and then if it's not, it doesn't make, and then the other being when you compare it again of
should we try to write some code for this? Or is this useless? So
can you just grab two images of the threes and then use like the real?
Yeah, I was just thinking to make it easy to not like, we can have 4 values, right? So you're saying, which makes sense in my head at the moment, that these two, if we're not careful, we could assume that these two are the same. So if we say does this work? Can I do a mean like that? I got to, maybe I have to import math or something. Does that work? No. Math dot. Sorry, I don't know this on the top of my head.
Wasn't there something like double shift or something like?
I don't think it's shift tab, double shift.
I think it was hitting shift twice or something like that.
Doesn't do it for me.
No, I don't know.
Tab also doesn't do it. Shift tab also doesn't do it. Oops, that also didn't do it. I think it's something no, A10. Oh God, median, come on. That's probably on the list.
Python math mean list.
Maybe it's even on the list function. No, okay. Python list mean. Python lister mean.
Yeah, that's just gonna say average the sum of by the length.
Yeah, but I know there's like some functions, isn't there? Wow, they actually make it. They actually code it. Seriously? Math? Because it's such a simple calculation, or what?
Yeah,
All
so
right.
you have to import. It says from statistics import mean.
Okay. And then I can do mean and pass it in.
Yeah.
Okay. All right, so this would be 0.25, and then this would be 0.25 too. All right, we gotta print them. Yeah. So if we would just take the total mean of each of the images, that's not a great way to go.
No.
But if we compare each of them, like this one to this one, we say they're okay. We have to kind of keep track about like how much is the difference, right, on each spot, and do something with that. Like if we add up all the differences, right,
yeah,
and then we have a.
So if let's say to make it even simpler than that, if we have a threshold, right, of these where you say, like, you know, comparing 0.5 to 0, right, first index, or the 0th index, right? Let's just say there's like this threshold gate, right? The gate returns false. Okay, so that's what I'm saying is we can compare each of these, like write a function where you loop through the entire, you're comparing two images, so you take these two as inputs, and as you're looping through each of these, there's this threshold gate where if it's true, if it's similar, it's true, and then you just increment a true number, and then there's a threshold on that true number, where
that will work.
If there was, you know, the true number has to be less than 10, and then you know it's, you know,
that will work.
True.
Or you collect for each pixel, which is what I was trying to say here, which I think should still work, right? Like you collect the difference for each individual pixel and you add them up, and then you have a threshold for that number. Because if we look at each of those in here.
Yeah, because I think this goes back to what I was saying before, is you're going to get a difference of 0.5, a difference of 0.5, a difference of 0.5, and a difference of 0.5.
Yeah, but I add all of those together.
Uh-huh.
And if I would have then a list 3, that is the same as list 2, I get nothing. There's no differences.
Yeah, that could also work too.
Right?
Mm-hmm.
So that would work as long as we don't take an overall average of both of the images, but just on a per window or per pixel, just on a smaller, like if we go per pixel, we get it very precisely. If we go on a per window basis, it's a bit more blurry, but it should be fine too, I think. I mean, I can write this too, but well, I think we got it. I think it makes sense not to put this time into that. Yeah, I'd say this is something how this could work. How can we determine this distance from our ideal 3? We could just add up the difference between the pixels of this image and the ideal digit. Some differences will be positive while others will be negative, and these differences will cancel out, resulting in a negative. Okay. Resulting in a situation where an image that is too dark in some places and too light in others might be showing as having 0 total differences from the ideal. So this is what you were saying essentially, right?
Mm-hmm.
But why? To avoid this, there are two main ways data scientists measure distance in this context. Take the mean of the absolute value of the differences. Right, this is what I was thinking. Absolute value is the function that replaces negative values with positive values, yeah. This is called the mean absolute difference, or L1 norm. Right, this is what I was thinking. Take the mean of the square of differences, which makes everything positive, and then take the square root, which undoes the squaring. This is called the root mean squared error, or MSE, or L2 norm. Okay, it's okay if you have forgotten your math, thank you. In this book, we generally assume that you have completed high school math and remember at least some of it, but everybody forgets some things. It all depends on what you happen to have had reason to practice in the meantime. Perhaps you have forgotten what a square root is or exactly how they work. No problem. Anytime you come across a math concept that is not explained fully in this book, don't just keep moving on. Instead, stop and look it up. Make sure you understand the basic idea, how it works, and why we might be using it. One of the best places to refresh your understanding is Khan Academy. For instance, Khan Academy has a great introduction to square roots. All right. Distance 3. So it takes the A3 image minus the mean of the 3 images, takes the absolute value, and then the mean of that. Square root. Okay.
Uh-oh.
Martin forgot to run something. So this is just picking out an example image.
Mm-hmm.
Okay. .1. And these are going to be much bigger.
Right.
Yeah. Cool. Because it's a 3 that we're comparing to the mean of the 7s in that case.
Mm-hmm.
In both cases, the distance between our 3 and the ideal 3 is less than the distance to the ideal 7. So a simple model will give the right prediction in this case. PyTorch already provides both of these as loss functions. You'll find these inside torch.nn.functional, which the PyTorch team recommends importing as F, L and F, and is available by default under that name in Fast.ai. F, L1 loss. Okay, I'm gonna go get some water now and you can continue.
Sure.
You can't scroll. I can give you access remote control.
Yeah.
Nick Trumpokis. There you go. You got it?
Requesting now.
You shall, you may. Okay, just gotta go get something. Be back.
Okay, cool. So PyTorch ready, blah, blah. That's F. F.L1 loss A3.float. Okay, let's run this. MSE loss. So here MSE stands for mean squared error, and L1 refers to the standard mathematical jargon for mean absolute value. In math, it's called the L1 norm, okay? Intuitively, the difference between L1 norm and mean squared error is that the latter will penalize bigger mistakes more heavily than the former, okay? And more lenient with smaller mistakes, got it. When I first came across L1 thingy, I looked it up to see what on earth it meant. I found on Google that it is a vector norm using absolute value, so looked up vector norm and started reading. Given the vector space V over field F of the real or complex. Okay, this is a lot of stuff. We're just gonna skip all of this. Like the L1 loss is just equal to A minus B absolute, where A and B are tensors. I'll make sure in this book that every time some mathy jargon comes up, I'll give you the little bit of code it's equal to. Okay, awesome. Thank you, Jeremy. We just completed various. You've done some numerical programming in PyTorch before, and you may recognize these as being similar to NumPy arrays. Let's look at this very important data structure. All right, let's look at this. Okay. Okay, so this is just explaining what NumPy is, and very similar API to that provided by PyTorch. However, does not support the GPU or calculating gradients, which are both critical for deep learning. Therefore, in this book, we will generally use PyTorch tensors instead of NumPy arrays where possible. Okay, so I could drop this link to the video again in the chat. Anyone interested? There's a section on that goes further into this NumPy arrays versus PyTorch tensors. Okay. Note that Fast.ai adds some features to NumPy and PyTorch to make them a bit more similar to each other. If any code in this book doesn't work on your computer, it's possible that you forgot to include a line like this at the start of your notebook. Fast.ai Vision Import, okay? But what are arrays and tensors, and why should you care? Okay. Python is slow compared to many languages. Anything fast in Python, NumPy, or PyTorch is likely to be a wrapper for a compiled object written and optimized in another language, specifically C. In fact, NumPy arrays and PyTorch tensors can finish computations many thousands of times faster than using pure Python. Hello, you're back.
Hi.
So
what did you learn?
We're just going over what NumPy is.
This is what we listened to before.
Yeah.
Mm-hmm.
So I guess we skipped ahead a bit.
Cool.
Biggest difference is that NumPy doesn't optimize or can't use the GPU for calculating gradients, and PyTorch does, which is why we're using PyTorch.
Right.
Cool. So NumPy array is, let's see.
Did Fant just control my screen? Did you do anything nasty?
I mean, you'll probably find out later when you're doing timestamps for this video. Okay. A NumPy array is multiplied. Okay, since that can be any type, they can even be arrays of arrays, with the innermost array potentially being different sizes. This is called a jagged array. By multi-dimensional table, we mean, for instance, a list, dimension of 1, or table or matrix, dimension of 2, a table of tables, or cube, dimension of 3, and so forth. If the items are in the most simple type, such as integer or float, then NumPy will store them as a compact C data structure in memory. Okay, this is where NumPy shines. You want to say something?
No, sorry.
Oh.
Keep going.
All right. NumPy has a wide variety of operators and methods that can run computations on these compact structures at the same speed as optimized C, because they are written in optimized C. That was a silly sentence. a PyTorch tensor. Okay.
Yeah, we listened to Jeremy talk about this.
Yeah, let's scroll past all this.
Go ahead.
Here we go. To create an array or tensor, pass a list or list of lists, blah, 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 to array or tensor. Let's just run this.
Yeah, we saw him do that too. So, but yeah, go ahead.
All right. I'm just going to run.
And then he's just making this array and it comes out as an array.
Oops.
Bye. Tensor looks the same. Can get pieces of the tensor, 0 indexed, so we could get the first row, I guess, with 0. And then the columns, right? So the first item before the comma is the columns, and the second item is the rows. So this is 2 and 5. It's just weird because it's displayed like that now, but it's actually like that.
It's 2 stacked on top of 5. Yeah.
Yeah, 2 from the first row and 5 from the second row.
Right. Okay, you can combine these with Python slice syntax, start end with the end being excluded. So.
Okay, what is that? Let's make some fun quizzes. Can I wait? Let me make a quiz for you for a second.
Oh boy.
All right, close your eyes. Close your eyes. All right. So, okay. Is it? Well, it should be 0 indexed, right? And being excluded. Why does it have a 3? Okay. I guess. Well, I mean, that's not right. This is kind of a boring quiz, but go ahead. It's ready for you. Actually, still like that. What's that gonna print? Can we make this a bit smaller? I know how we can make this a bit smaller. Bye. Okay, there you go. So what's that gonna print?
So this is getting from, remind me the comma notation again. It's tensor, so 0, it's the first tensor. So the 1, 2, 3.
Yeah.
And then 1 to 2. So it's taking, so this should print 1 to 2. So this should print 2, 5.
No, I think it should just print 2. Yes.
So why didn't it print?
So it takes the first, like the first row, that's the 0.
And okay, so how does it do it with the second? Like, how does it do for
So these are columns, right? The one after the comma is going to be a column, and we're slicing the column, so we're not getting.
So I guess just my question is, make this print 2, 5.
2, 5.
Yeah.
Okay. I have to do like that, or just do this. I guess they should be the same.
Okay, so what we were seeing before then was just... Okay, so I misunderstood because I thought you meant when it was represented 2, 5, it was vertically across the tensors.
It was. It just created a new tensor out of it. which was because we said give us, I think, I don't remember how it was, but like now we're keeping, you see, like we're slicing, we're making, it's still two things in there. It's still two tensors. The other one, we combined it into one tensor.
Got it.
So
Okay.
I think, I don't know how we can recreate that. I forgot what it was. I think
So-
we just said, give us the second column. So, yeah. Totally blanking on it. So this, what is this going to give us? This is not going to be an error, yeah. Because we only have 0 and 1.
Yeah, I think it was just comma.
1, like that.
Try that.
No, then it's going to give us, yeah, then it's good. Okay, that works. That does not work because we
You
need
put
this.
Yeah.
Yeah.
Okay. That's what I was thinking was going to happen.
But the difference is that in the second time we did a slice on that other side. So we're saying, what was it? I think I
Yeah,
said
it was 1, 2, and then
1, 2,
0 was in place of
2. Like that, right?
Yeah, before the comma there was right.
Yeah.
Right. It
So
creates another tensor.
when we slice here, it doesn't make it into 1. Yeah, it doesn't just take out this piece here, but it just takes out this piece and this piece. Like of each per each row, it takes out. Interesting, yeah. Like one could assume that these are the same. I think you're right, because that's essentially what we're saying. But we're saying take a slice, and that's why it does that thing.
Yeah, interesting.
Okay, interesting. Maybe good to know. Maybe not.
I mean, I think it's good to know for like debugging, right? Because if you think you're doing the second version and you're just trying to get a single array of values,
right?
Not gonna happen, right? You're getting an array of arrays with single values.
Cool.
But if you did, so replace that 1 on 80. Yeah, replace that with a 0. Now you should be getting
1, 2, 4, 5. Yeah.
Okay. So interesting because you put. So it's really just because you put that colon there. It creates it as a slice. Because if you remove the 0, it's the same thing. Yeah. Okay.
Yeah, that should be the same. Yeah. Everything up to 2.
Cool.
And again, we have a cute face here.
So cute. It looks like some sort of like nocturnal creature.
Yeah, it does.
4 eyes.
I'm just going to keep this around because I think that was interesting. That we get something else like that. Okay.
Okay, carry on.
And you can use the standard operators such as plus, minus, times, divided, tensor plus 1. Then what does it do? It adds 1 to everything, right? Is that how this metrics stuff works, right? Yeah. Tensors have a type. Torch long tensor and will automatically change type as needed, for example, from int to float. Okay. So is our baseline model any good? To quantify this, we must define a metric. Ooh, we are being slow. Look at that. We still have a lot of stuff to go and it's already late.
Yeah, we may have to split this one into 2.
Yeah, I think so.
Or just next time not spend so much time learning.
No, I like this. This is fun for me.
No, I know.
I think I learned stuff
more
well like that. Yeah. It's more fun than just watching the videos.
Yeah, totally. Cool.
Yeah. Yeah, let's just split it up. We don't really have a rush. We're just gonna slowly go through this course.
Yeah. So where are we on now? Computing metrics
So
using broadcasting? Is that the next section or are you?
Yes, computing metrics using broadcasting is the next section.
Cool.
And then we have stochastic gradient descent, which is going to be interesting. 93 cells hidden. So my suggestion is we finish computing this one and then we do.
Agreed. Agreed.
Wow, this is 93, 56, 64.
It's a big, this
23.
is a big section. Yeah.
Maybe we split it up in 3. We'll see. But we can do this one definitely still today.
Let's do it.
Okay. Whoops. All right. So recall that computing metrics using... So we want to find out whether the baseline model is any good. Recall that a metric is a number that is calculated based on the predictions of our model and the correct labels in our dataset. In order, okay, so again, recall that a metric is a number that is calculated based on the predictions of our model and the correct labels in our dataset in order to tell us how good our model is. Okay. For instance, we could use either of the functions we saw in the previous section, mean squared error or mean absolute error, and take the average of them over the whole dataset. However, neither of these are numbers that are very understandable to most people. In practice, we normally use accuracy as the metric for classification models. As we've discussed, we want to calculate our metric over a validation set. This is so that we don't inadvertently overfit, that is, train a model to work well only on our training data. This is not really a risk with the pixel similarity model we're using here as a first try, since it has no trained components, but we will use a validation set anyway to follow normal practices and to be ready for our second try later. To get a validation set, we need to remove some of the data from training entirely, so it is not seen by the model at all. As it turns out, the creators of the MNIST dataset have already done this for us. That's why we had this folder. Do you remember how there was a whole separate directory? Yes, again, called valid. That's what this directory is for. So to start with, let's create tensors for our 3s and 7s from that directory. These are the tensors that we will use to calculate a metric measuring the quality of our first try model, which measures distance from an ideal image. Okay. Click. What do we do here? Valid 3 tensor torch.stack. Okay, so he's using again this list comprehension to open now all of the 3 images inside of the validation set directory for the 3s and saves all of them into this stack tensor called valid 3, and then converts them again to floats and divides by 255 to get everything between 0 and 1, and does the same thing for the 7s. And then we get this again. What's it called? Rank 3 tensor. 2 rank 3 tensors. It's good to get into the habit of checking shapes as you go. Here we see 2 tensors, one representing the 3's validation set of 1010 images of size 2228, and one representing the 7's of 1028 images of size 2828. We ultimately want to write a function is3 that will decide if an arbitrary image is a 3 or a 7. We do this by deciding which of our 2 ideal digits is arbitrary image of our 2 ideal digits this arbitrary image is closer to. For that, we need to define a notion of distance. That is a function that calculates the distance between 2 images. We can write a simple function that calculates the mean absolute error using an expression very similar to the one we wrote in the last section. He does this thing, which I find somewhat confusing, this one-liner Python functions. I don't think this is something that people see a lot outside of this.
I don't know. I remember when I was writing in Python, it was a lot of these like one-line Pythonic, very let's try to squeeze everything with minimal amount of spaces. And I found them frustrating because it was like unreadable, right? Including like the function and then the return on the same line, and just returning what the actual function is doing is kind of confusing. I mean, if you're reading through it rather quickly, it makes it very hard. Yeah,
especially if it's like in the previous example, there was something, I don't know if this was like that too. But if you have like a function definition, including its return value on one line, and then the next line is the function call.
Yeah.
This looks really unfamiliar.
Right.
But I mean, he said that too, that he's not really following Python like standards that much. Mm-hmm. Maybe there's some programming languages where this is very common. Anyways, for me, it's easier to read like this. And the function does MNIST distance from A to B, I guess, return. So this is going to be pixel value A minus pixel value B, take the absolute, take the mean, And then what is this? What is this? Like,
Are you asking me what the answer is?
no, what is -1 and -2 in there? I'm confused.
A
Like-
minus B.
Like
Return
it's
A minus
inputting
B,
like
absolute.
a tuple of two negative.
I don't know.
Like, this makes sense to me. Take two values as input. Subtract like one of the other. Take the absolute of it. Oh, well,
So-
that would be a mean.
Yeah.
What would be the mean? Yeah.
So I'm gonna take Jonah Vision's approach on this as well, since it's been working so far with us on this stream. I think if we read a little bit further, Jeremy has a way of answering Martin's questions.
You read. Go ahead.
No. I want you to read this one.
This is the same value we previously calculated for the distance between these two images, the ideal 3, mean 3, and the arbitrary sample 3, A3, which are both the single image tensors with a shape of 28, 28. Same value, distance between. Okay. But in order to calculate a metric for overall accuracy, we will need to calculate the distance for the ideal 3 for every image in the validation set. Wait, what? I totally got lost. The same value we previously calculated for the distance between these two images. Two images, distance. The ideal 3 and mean 3, and the arbitrary sample A3. Okay. Both single image tensors with a shape 28, 28. But in order to calculate a metric for overall accuracy, we will need to calculate the distance to the ideal 3 for every image in the validation set. How do we do that calculation? We could write a loop over all of the single image tensors that are stacked within our validation tensor set tensor, which has a shape of 1010, 28, 28, representing what that's what I would have thought, but there's a better way. Something very interesting happens when we take this exact same distance function designed for comparing two single images, but pass in as an argument valid 3 tensor, the tensor that represents the 3's validation set. Okay, so it just applies it to all of them. But this doesn't, Jonah Vision, Nick, this doesn't explain that so far, may I say. Do I have to skip forward still? Because so far, yes, I agree, but I still don't know what that's about.
Keep going.
Is it coming or what? Okay, good. Be quiet and read. Wait, it doesn't work. Okay, instead of complaining about shapes not matching, it returned the distance for every single image as a vector. For example, a rank minus one tensor.
No, I think that's just a rank 1 tensor, because it was rank minus 3.
Oh,
Yeah.
right. Thanks. Of length, yeah, right. Yeah, there's just one thing in here. Of length 10, 10. The numbers of 3's in our validation set. How did that happen? They can either look at our function mnist distance and you see of the okay, there it is. And you see we have there's the subtraction a minus b. The magic trick is that PyTorch, when it tries to perform a simple subtraction operation, no, it's not yet. Between two tensors of different ranks, we will use broadcasting. Nice. I'm so sorry. That is, it will automatically expand the tensor with the smaller rank to have the same size as the one with the larger rank. Broadcasting is an important capability that makes tensor code much easier to write. After broadcasting, so the two argument tensors have the same rank. PyTorch applies its usual logic for the two tensors of the same rank. It performs the operation on each corresponding element of the two tensors and returns the tensor result. For instance, tensor 1 to 3 plus tensor 1 1 1. There's no broadcasting involved here though, right? So in this case, PyTorch treats mean 3, and not in this case, in the case up there. A rank 2 tensor representing a single image as if it were 1010 copies of the same image. And then subtracts each of those copies from each 3 in our validation set. From each 3,
Okay.
Image 3. What shape would you expect this tensor to have? Oof. Try to figure it out yourself before you look at the answer below. I'm going to take a sip of the tea and let you do that.
So in this case, PyTorch treats mean3, a rank 2 tensor representing a single image, as if it were 1,010 copies of the same image, and then subtracts each of those from those copies. Subtracts each of those copies from each 3 in our validation set. What shape would you expect this tensor to have? Did you look at the answer?
No, I didn't. I don't know the answer. My brain's switched off at the moment. I'm just giving you. I'm just letting you do it. I'm just letting you do the thinking work while I have a sip of tea.
What was that? You have a cuckoo clock?
Oh, this is my phone's weird. Like, it keeps, like, when my computer connects to the data plan on my phone, like it makes this noise, but it keeps connecting and disconnecting for no apparent reason. I don't know why.
Interesting. It was just you said your brain turned off at the
And
moment, and then it just went. Okay, so in this case, PyTorch. So it treats mean3, a rank 2 tensor, single image, as if it were of the same image. Okay, so it's still a rank 2 tensor, and then subtracts each of those copies from each 3 in our validation set. I would think it was still a rank 2 tensor.
Why is mean3 a rank 2 tensor in the first? Because it's 2828, and it's one image. 2828 makes the 2 dimensions, the 2 ranks. Is that right?
I don't know. Scroll down.
Oh dear. Wait, so you're giving up, huh?
I think it's a rank 2. I think it's a rank 2 tensor. Ooh.
Rank 3. It's a rank 3 tensor, Nick. You were so wrong. I knew it all along. Okay, so let's see why. We're calculating the difference between our ideal 3 and each of the 10 3s in our validation set for each of 2828 images, resulting in the shape 10 2828. There are a couple of important points about how broadcasting is implemented, which make it valuable not just for expressivity, but also for performance. PyTorch doesn't actually copy mean3 10 times. It pretends it were a tensor of that shape, but doesn't actually allocate any additional memory. It does the whole calculation in C. If you're using a GPU in CUDA, the equivalent of C on the GPU, tens of thousands of times faster than pure Python, up to millions of times faster on a GPU. This is true of all broadcasting and element-wise operations and functions done in PyTorch. It is the most important technique for you to know to create. It is the most important technique for you to know to create efficient PyTorch code. How do you read emphasis? How do you read emphasis? Do you just tilt your head slightly?
Mm-hmm.
It's the most important technique for you.
Whatever noise comes out.
To create efficient PyTorch code. Next, in MNIST distance, we see apps. You might be able to guess now what this does when applied to a tensor. It applies the method to, there it comes finally. I haven't been able to concentrate at all because I was waiting for it to each individual element. Still not. It applies the method to each individual element in the tensor and returns a tensor of the results. That is, it applies the method element-wise. So in this case, we'll get 10 met. Oh, maybe this is binary, huh? Maybe it's actually 1, 2, 4, 8. This is 10. I guess the stream has been going too long. I'm getting all loopy and stuff. Finally, our function calls mean -1, -2. The tuple -1, -2 represents a range of axes. Okay. In Python, -1 refers to the last element, and -2 refers to the second to last. So in this case, this tells PyTorch that we want to take the mean ranging over the values indexed by the last 2 axes of the tensor. Holy what? So in this case, we want to take the mean ranging over the values indexed by the last 2 axes of the tensor.
Okay, the last two axes are
The
the
28,
horizontal
28.
and vertical
Right?
dimensions. Yeah.
Okay. What a weird way of saying that. Okay.
Anyway.
After taking the mean over the last two axes, we're left with just the first tensor axis, which indexes over our images, which is why our final size was this. In other words, so it cuts those out, like it computes them and then gets rid of them. In other words, for every image, we average the intensity of all the pixels in that image. Oof. I get it that this is what we did, but maybe I'm just too tired. But
yeah, it seems like a weird way of doing it with this in this way, but
I should probably
could
just
also
read
just
this
be
again
tired.
tomorrow and then see.
Fresh eyes.
Okay, fine. We'll be learning lots more about broadcasting throughout this book, especially in secret, and we'll be practicing it regularly too. We can use MNIST distance to figure out whether an image is a 3 or not by using the following logic. If the distance between the digit in question and the ideal 3 is less than the distance to the ideal 7, then it's a 3. This function will automatically do broadcasting and be applied element-wise. That's easy because we just have a classification between two things, essentially, in this case. Like we don't have to, we're not doing dog breeds, we're just doing dog or cat.
Right.
Yeah. Just like all PyTorch functions and operators. Sorry, Jeremy. Define is 3x, return MNIST distance. Okay, that's using the function we defined before. If it's smaller, if it's a 3, if the distance to the mean 3 is smaller than the distance to the mean 7. Nice. Let's test it out on our example case. Is 3 a3? Is 3 a3.float? I like that. This really reads like a sentence. Is 3 a 3? True. 3 is a 3. Note that when we convert the Boolean response to a float, we get 1.0 for true and 0.0 for false. Thanks to broadcasting, we can also test it on full validation sets of 3s. Is 3 valid 3 tens? Many trues. Cool.
Ooh, one's a false.
Oh. The second to last one. Second to last one.
So can we see that second to last 3?
Maybe. So that would be a validation set. We'd have to look for, can we grab it like that, do you think? 3 tens. There it is. And then probably, oops, sorry, we get minus second. It's 1 tensor. So let's try to display it, huh?
Yeah.
What was that? Show image. Where is it? Oh, there it is.
Interesting.
So it thinks that that's a 7. It's a weird 3.
Yeah. Anyway.
Interesting. I wonder why, because like maybe.
Well, so if you take the top swoopy part and you move it over, right?
The top swoopy, if you move it just a little over, then it would be a 7. Yeah.
Part, and you move it over, so it
Look,
connects.
no hands.
That would be a 7.
Yeah.
And then only this part is invalid.
And that just isn't enough in this example.
Right.
Yeah. Interesting.
All right. You can take control back of your screen.
Thanks. You keep the option of doing stuff. Now we can calculate the accuracy for each of the 3s and 7s by taking the average of the function for all 3s and its inverse for all 7s. Because it's just two things, so Now we will need to define a function for the sevens. Makes sense. Is 3 valid 3 tensor float take the mean? Accuracy 7, 1 minus is 3 valid 7 tensors float mean. Accuracy 3 is 0.9, accuracy 7 is 0.98. Overall accuracy 0.95. This looks like a pretty good start. We're getting over 90% accuracy on both 3s and 7s, and we've seen how to define a metric conveniently using broadcasting. But let's be honest, 3s and 7s are very different looking digits, except for this one. And we're only classifying 2 out of the 10 possible digits so far. So we're going to need to do better. To do better, perhaps it is time to try a system that does some real learning on the next stream. That can automatically modify itself to improve its performance. In other words, it's time to talk about training process and stochastic gradient descent. So let's not do this today, but I'm interested to see, we can play around a little more. Like, how many do you think, you want to guess how many are in there?
Oh, out of, how many was it? 10? How many out of 1,000?
You have an accuracy, what was it, 0.91? Can you do that math in your head?
I mean, that would just mean that there's like 90 of them that are invalid.
Is that what it means?
Like 89.
Like 10 would be right. So let's see. So can I do res dot count false? Does that work? Nope. Res. How do you think we can do that?
What is res?
It's just this tensor. I just assigned it to a variable.
Oh, okay.
And so it is a list. It's a tensor of trues and false, but I think it's one dimensional. Res dot, what was that? N shape. N. How do we get that? N.
That tensor.
Or just shape. It's shape actually.
The tensors with booleans, or are those? Can you count them as strings? Can you count?
I'm pretty sure they're booleans, not strings, because it said something before.
Yeah.
It said something before that you can represent them as floats as well.
I know, but Python, everything kind of mixes together. You don't care about types. Python.
Hey, let's not start this. So res.shape, so it's a one-dimensional tensor. So this is essentially just a list. I think I can probably be hacky.
Oh, yeah. Jonah Vision was saying, try just summing the whole thing. Trues will equal 1.
But, okay, interesting. I like that. Right. Res, and then
that's it.
926, and then we got, can we do a length of the res probably? 84. Okay. So that would mean that makes sense. 84.
So my guess was what, 89? Yeah, not bad.
No, I think you said 90 something.
Bring it back.
Close enough.
Close enough.
Cool. Could be interesting to look at some of them, but whatever. Enough for today, I think, right?
Yeah, I'm pretty tapped out for today. Yeah. All right. Cool. So next time we're going to jump straight into stochastic gradient descent. With 93 hidden cells.
Scary.
I think
we can do it.
Yeah.
Maybe we're just going to have one session on stochastic gradient descent and then do the rest in another one. We'll see how deep we dive with this one.
I think we just need to remember that if we read a little bit further, Our answers, the solutions will reveal themselves. Yeah.
But it's great. It's a great learning thing for me because I'm like, why, and then there's the answer. So my brain's like all primed for picking it up, putting it in the right places.
It's so great.
Oh, that's fun. Yeah, that's more fun than watching the videos, I think.
Yeah.
I like it.
Yeah. So Jonah Vision was suggesting maybe do some pre-learning on YouTube for gradient descent. I think that's valid. We should probably,
would be a good idea.
Yeah. Maybe we could also just do pre-learning on like lesson 3, right? With and then just.
But like one of the, I get it, but like one of the things is also that we're like trying to pretty much like stream our whole learning process here for this, right?
That's true. We're not trying to teach this.
Yeah, it's more like how, like what actually goes into understanding this topic, right? Yeah. And so I don't want to do too much, side stuff where then I even recorded the cleanup sessions for the notebooks that I did, and we're going to upload them to YouTube just to have like all the steps more or less documented, I guess. Or we're just lazy. Depends how you want to say it.
Yeah. Well, either way. So the only thing that tells me is that it's either going to be 1 section or 2 sections on the next stream. All right. Cool. So until next time. Thanks for hanging out.
Awesome. Oh, wait. Just a second.
Yes.
Jonah Vision, do you want to tell us how you did the deployment? I'd be up for that.
Sure.
If you want. We could try it out. What do you think about that? Or next time?
You want to get on?
I don't know how we would do that. I could like just type whatever or do whatever instructed.
Yeah. You want to get into the other collab?
Yeah, I could do that. Is it?
It was Binder and collab, right? And GitHub and everything. So you want to?
You're up for doing that? Both of you?
He said, yeah, give me a sec. So
cool. Let's try it. It's a little add-on. I can just open this. Let me go to. Production Rex. Wait, which is, that's the one we tried.
Yeah.
Maybe it's easier like that. I think I can open it in here. I'm really curious what my binder, what we messed up there last time.
So saying, okay, I don't know if I could copy this.
This is not working.
So Jonah Vision saying that adding this like one line for NB convert in the requirements.txt.
Oh, really?
Yeah.
Okay. Huh.
So maybe it doesn't even make sense to open up all of this stuff. Just open it up in Drive and in GitHub.
If it's just that's true. If it's just a requirements.txt file.
Yeah. Or like
we don't need to edit anything otherwise.
No, I think that's all Jonah Vision did.
Okay. So we had that in a different. I remember everything's coming back. Dog voila. Okay, what was it?
So NB convert greater than equal to 6.0.0.
Like that?
Yep.
Okay.
And then Jonah Vision's also saying that they had fast core as well.
I saw that in one of the things that we. What is fast core? Okay, let's just add it. So NP converted fast core, does that have any specific version number? Or it's just fast core?
I don't know.
No,
I'm
okay.
only seeing fast core, but let's see if this works. Put it on binder.
Right, so to remember
Yeah,
this, we need cool. So we need this GitHub dog voila main. This in the way. We need URL.
Good job.
Thanks. Remembering the important stuff. So, and we want to do dog breed classifier. I know you're not going to load. Why is this saying? Anyways. And then we have to put in, what was it? Voila, render, I think. Right? Like this?
I think so, yeah. Just, yeah. Get rid of one of those. Yeah.
Okay. Main, URL, launch. And just because out of tradition, I'm going to chat it to you. This is exciting.
Yeah.
I'm going to be much more motivated to clean up our desktop classifier if that works. Okay. Nothing else to say, huh, in the meantime?
At least music is playing this time.
True.
I think. I'm seeing Spotify source bouncing around in OBS.
I can show a quick preview of my cleanup video. Like it's sitting here on my Windows desktop.
You took that photo, right?
No, a friend of mine, yeah.
Nice.
Oops. Look at this beautiful going over everything. I'm mostly just deleting. Oh no, this is interesting. I figured out how to make a nice
table in
nice table, yeah, because it wasn't rendering the table because it's some still going on.
Yeah, I have it as a separate window here, so I'll just tell you when it's done.
Mm-hmm. I'm talking over all of it. I don't think you can hear that now. But it looks nice now. I don't know if you checked it out, Nick. But look, I also put links up there.
This is in your
it's in our GitHub.
Oh, it's on our GitHub. Okay.
Yeah, this is what the notebooks look like. Like I've just been updating the notebooks in here.
Nice.
So that's intro 01 intro. Now looks like that. If it manages to load.
A lot of loading.
He really doesn't like that. What about you?
Binders
Is
also
it stuck?
say your session is taking longer than usual to start. Check the log messages to see what's happening, but it's just it was uninstalling NB convert, and now okay, now it's moving forward. It's on 48 of 48, pushing the image. Okay, now it's pushing
Mhm.
all the images.
Yeah.
Cool.
Do you still have the cat and dog image? There it is.
You still have this other.
Still have them sitting around. I didn't trash my downloads folder since last time.
You still have this video overlaid. I don't know if.
What? Where? What video? I don't see it myself.
Okay, hold on. Let me see if I can get rid of it.
Okay, go for it. Do what you must.
It's weird. It's not.
Wait, let me try.
I'll do it.
Maybe I just need to do this. Is it gone now?
Nope. It's still there.
Gonna open it up and close it. What about now?
It's still there. It's like your screen is just maybe stop sharing and then reshare. Yeah, I think it just froze on your screen share.
Okay.
Yeah.
What
there we
about
go.
now?
Perfect.
Okay. Oh, and this is also advancing finally. We've waited a lot of those cycles last time.
Yes, we did. This is what took the longest last time.
So, John Vision, where did you how did you find this missing dependencies? I think I remember seeing them in one of the example repos that we looked at, but it didn't seem to be inside of the one that they were running with the bear classifier. Or was it? Isn't that the one that we picked up?
Jonah Vision saying that they saw it in Fastcore and somebody else's, and then they just thought about adding NB convert. So.
Because here it's not in there.
Okay, so it just pushed it, and now it's launching the server. Cool. Let's see if this worked.
What's that? Copy the text below and pasted a new read to show a binder badge. Oh, cool. Sure, let's do it.
I think in the last stream you saw that same thing and you were like, that's silly.
Well, changed my mind.
I see that.
I'm not gonna mess it up if you make a readme now, huh? No, it already pulled it, the state. It's not connected to the GitHub repo. Let's not do it anyways.
Don't touch it.
Just
don't break it. Don't step away from the computer.
I'm gonna put my hands on the mic.
Okay, cool. Sweet. Let's see if it works.
Is that all? No, okay, wow. All right, we had that working. Upload, dog, open, classify. Wow.
Nice.
It's working.
Yeah.
Labs
awesome.
for Jonah Vision. Thanks so much.
Thank you.
This was, oh my God. Beautiful. Look at this. The Brittany Spaniel cat. Wow. Very happy. Thank you. Okay,
Yes.
That's really nice. So we have this actually functioning.
Sweet. Very cool. All right.
All right. That's a success. I like ending things with a success.
Yep. All right, cool. So let's maybe on Friday, I don't know, do you want to continue with the gradient descent? Do you want to
Yeah.
Yeah. Okay.
Yeah, let's do that.
Cool.
More gradient descent.
Oh, look at that little badge right
Oh,
there.
that's the bear one,
Oh,
but we
that's
can
the bear one.
we can have the same. We can have it really fast.
All right.
Look at that. I believe. And then we can make it nicer later on. Add badge.
Binder badge. Yeah.
We just earned a badge.
What?
We can proudly display it. There it is. Look at it.
Wow.
Launch binder. Oh no. Does it have to do it again?
I don't know. Don't.
Okay, anyways, we're not gonna this is not happening.
Enough for today. Thank you very much.
All right. Yeah.
See everybody on Friday.
Bye.
Bye bye.